So good day everyone, we are the group 6 and for these lessons we will be discussing about carboxylic acids, esters and related compounds. So we will first discuss the carboxylic acid, its nomenclature, properties and acidity, and its conversion to esters. So what are the carboxylic acids? So the carboxylic acids are a classification of organic compounds and are the most important functional group presented by a carbonyl group, which is the CO, and attached with a hydroxyl group, which is the OH. So this one here is the structure of a carboxylic acid. So it has a general form of carbon bonded to an oxygen with a double bond, and it is also attached to a OH, which is the hydroxyl group. So the R here represents the side group or the rest of the molecule, which will be either the carbon or the hydrogen. Nomenclature of carboxylic acids. So according to IUPAC, there are some steps to follow in naming the carboxylic acids. So we will derive the IUPAC name of carboxylic acids from the name of the longest carbon chain that contains the carboxyl group. So the first step is to number the chain beginning with the carbon of the carboxyl groups. The second step is to drop the final E suffix from the name of the parent alkane and replace it by the IOC acid or ioic acid. So we will have this structure, for example. So this oxygen bonded with carbon and attached to a hydroxyl group is our carboxylic acid. So the first thing we must do here is to number or count the chain beginning with the carbon of the carboxylic group. So we can see that the longest carbon chain that contains the carboxyl group has a 6 carbons. So therefore the parent alkane is a hexane. So the next step is to drop the final E from the name of the parent alkane and replace it by ioic acid. So the E from the hexane, we will replace it with ioic acid. So now we have the IUPAC name of hexanoic acid. When a carboxylic acid also contains an OH or a hydroxyl group, we will indicate its presence by adding the prefix hydroxy. So we can see here that the hydroxyl group is presented at the 5th chain of carbon. So therefore, it has a IUPAC name of 5-hydroxyhexanoic acid. So the common name for aliphatic carboxylic acids are often derived from the name of a natural substance from which the acid could be isolated. So we have here an example of a common names of the IUPAC name. Like for example, methanoic acid, its common name is called formic acid. The ethanoic acid is another term of acetic acids, and so on and so forth. So next is the properties of the carboxylic acids. So most of the properties of carboxylic acids are a result of the presence of the carboxyl groups. So the first properties of carboxylic acid is its boiling point. So it says here that the greater the number of carbons in the molecule, the higher the boiling point of a carboxylic acid. So we have methanoic acid and ethanoic acid as a example. So the ethanoic acid here has a higher boiling point compared to the methanoic acid. Why? Because we can see in this chemical structure that the ethanoic acid has a greater number of carbons. It has 2 carbons, yes, and the methanoic acids has only 1 carbon. So we can say that ethanoic acid has a higher boiling point compared to the methanoic acid because the greater the number of molecules, the higher the boiling point of a carboxylic acid. Second is that the boiling points of a carboxylic acids are higher than the alcohols of the same number of carbons. So we have here the ethanol and ethanoic acid as an example. So we can say that the ethanoic acid has a higher boiling point compared to the ethanol. Why? Because as we can see here, the ethanoic acid has 2 oxygen, and we know that every oxygen contains 8 electrons, while the hydrogen here in ethanol contains only 2 electrons. So therefore, the ethanoic acid has a higher boiling point compared to the ethanol. So the second properties of a carboxylic acid is its solubility in water. So the first is the small molecule carboxylic acid such as methanoic acid and ethanoic acid is soluble in water. So in this statement, take note that alkenes, and esters are insoluble in water. So only the carboxylic acid with small molecules are soluble in water, and alcohols are also soluble if it has a small molecules. So next is that the solubility of a bigger acids decreases as the size of the molecule increases. So for example, we have here a chemical structure of a hexanoic acids, and it says here in this statement that the bigger the size of a molecule, the lower the solubility. So take note that every OH or hydroxyl group is soluble in water and every carbon chain is insoluble. But in this case, we can see that the OH group of hexanoic acid is just a small part of the molecule, while the other carbon chain has a major parts and has a long carbon chains. So if the carbon chains becomes very long, the solubility will decrease and it will make the carboxylic acid insoluble. So therefore, the solubility of the hexanoic acid is very low, making it insoluble.
Acidity of carboxylic acids. Carboxylic acids are weak acids because they only partially ionize in solution. They do not contain large amount of H positive ions, and their solutions do not contain many hydrogen ions compared to a solution of a strong acid at the same concentration. The strength of an acid is measured by pKa, that will be small letter p and the capital K and the lowercase a, which is a number that shows how weak or strong the acid is. The pKa value is the negative base 10 logarithm of the acid dissociation constant, which is the symbol Ka of a solution. If an acid is strong, then it will have a pKa of less than 0. The lower the value of pKa, the stronger the acid and the greater its ability to donate its protons.
Conversion of acid to ester. Esterification happens when carbolic acid reacts with alcohol in the presence of an acid catalyst, generally HSO, to form compounds called esters. Ester is one of the carboxylic acid derivative, wherein the hydroxyl part of carboxylic acid. So, originally carboxylic acid is RCOOH. The hydroxyl part of this carboxylic acid has been replaced with an OR, so that is an esters, its carboxylic acid derivative. And they are formed by esterification, and this is the reaction of carboxylic acid with alcohol in the presence of an acid catalyst, usually sulfuric acid. So the mechanism for esterification is as follow: the hydroxyl group from the carboxyl part of the carboxylic acid exchange place with the OR group of the alcohol. So this is the carboxylic acid and this is the alcohol. The hydroxyl part reacts with the hydrogen as to produce water, and since with this open linkage between this carbon atom and the oxygen here is sila yung magko-connect, so that will be the ester RC double bond O R, and with that ester will always have an acid part, yung merong double band OC, double band O, and it will always an alcohol part, the OR. So example would be the reaction of acetic acid. This is the acetic acid. It has 2 carbon atoms. And methyl alcohol will have 1 carbon atom, so mechanism will be the OH from the acid part, or the acetic acid, and the hydrogen from the alcohol will come together or will bind together to form water. And with this open band here as well as in this part of the alcohol, so this one will form linkage and they are going to produce the ester. So the CH3C double band O is the acid part and OCH3 is the alcohol part. So always bear in mind that esters will always have acid part. The series of carbon atom with the C double band O, or the carbonyl, and the alcohol part with the series of carbon atom with oxygen. So how do you name esters? They are usually named as alkyl carboxylate, wherein the alkyl is the name or is the part of alcohol reactant. So usually they are named as alkyl alcohol, like methyl alcohol, ethyl alcohol, so that alkyl name will be adopted, and the carboxylate part is the eventually the part wherein the IC acid from the acid name will be dropped and replace it with ATE. So let's have the rule. So name the alcohol part of the ester appear first. So unay natin pangalanan yung alcohol part, and usually they are on alkyl's name, so they should end with YL. So the name of alcohol part is simply the name of the R group of the alkyl or cycloalkyl or aryl. So that is the OR portion of the ester. And then we have rule number 3. The acid part of the ester is obtained by dropping the IC acid in the ending of the acid name and replacing it or adding the suffix ate. So, this is an esterification reaction between ethanoic acid and methanol. So, mechanism is the OH and the H will come together to form water, and the OCH3, this part of the alcohol, will be bind with the remaining part of the acid such that esters will be formed. So that reactant acid name is ethanoic acid and the alcohol name is methanol or methyl alcohol. In naming, this one will adapt the methyl, so that this is the methyl because that the alcohol part and the rest would be coming from the acid name. We are dropping the IC acid and add ATE, so that ethanoic acid will become ethanoate. The IUPAC name of the ATE of the esters proteus is methyl ethanoid. There should be two word here, so space would be found in between the name of alcohol part and the acid part. For the common name, it will still be methyl because it's an alkyl methyl acetate. We are not going to adapt the ethanoic because we'll have a common name of acetic acid. Dropping the IC acid and adding the acetic acid will become acetate. So methyl ethanoid is the IUPAC and the common name is methyl acetate. The alcohol part and the rest would be coming from the acid name. We are dropping the IC acid and add ATE, so that ethanoic acid will then become ethanoate. The IUPAC name of the ATE of the esters proteus is methyl ethanoid. There should be two words here, so a space would be found in between the name of alcohol part and the acid part. For the common name, it will still be methyl because it's an alkyl methyl acetate. We are not going to adapt the ethanoic because we'll have a common name of acetic acid. Dropping the IC acid and adding ATE, the acetic acid will then become acetate. So methyl ethanoid is the IUPAC and the common name is methyl acetate. Physical properties of esters. In general, esters have a pleasant fruity flavor and they are usually used as an artificial flavorings and perfumes. Esters are colorless, pleasant-smelling liquids, while those of higher acid are colorless solids. Lower esters are fairly soluble in water. The solubility of esters in water decreases rapidly with increase in the mass. The boiling points of methyl and ethyl esters are lower than those of the corresponding parent acid.
Chemical reactions of esters. The chemical reaction of esters that we're going to tackle is the reaction with water, which is the hydrolysis. So from the word hydro, which means water, and lysis, which means to break. The first type of hydrolysis that we're going to look at is acid hydrolysis. So this is the one that must be done under the acidic conditions. We start off with our ester, and we usually do this in the presence of an aqueous acid, so that means there is also water present, and in this case it's the water that's reacting with the ester, so we use aqueous acid and also be done under reflux conditions, and the products that we get this are the carboxylic acid and the alcohol. So the ester that shows here is this one, which is the ethyl acetate that is going to react with water under aqueous acid conditions. So we're just gonna go for hydrogen ions and reflux. Now let's have a look at what carboxylic acid made this. So in this case, this part was the carboxylic acid parts. As you can see, that would be the acetic acid, and the alcohol that makes it this part here, so that would be the ethanol. As you can see, this water molecule has been added across over here, and that's the hydrogen from the water, and that's the hydroxide from the water as well. That's what we do acid hydrolysis. So this is technically a reversible reaction and is reversible to acid hydrolysis of the ester. Now let's have a look at the same ester but having that undergo alkaline hydrolysis, or can be called as saponification. So alkaline hydrolysis is done in the presence of alkali, so we usually do it in the presence of a metal hydroxide, and the general equation for this is now ester plus alkali, and the conditions you need for this are reflux and the aqueous acid here, and again reflux conditions. In this case, we are not going to form the carboxylic acid but the carboxylate salts, and we'll show you why this is the case when we do this example and we form the alcohol as well. The ester that shows here is the same ester as before, which is the ethyl acetate, and the alkali that is used is the sodium hydroxide. Again with the aqueous under reflux conditions, and now we're gonna form the carboxylate salt because we've got a sodium ion here, and the carboxylate salt is from the carboxylic acid, still like that. So looking at it, it's the carboxylate salt, which is the sodium acetate, and so we reduce up that part and the sodium, which means we're left over with CH2, CH3, and OH, and that's going to form our alcohol, which is again our ethanol. Now as you can see, we now get different products even if it's the same ester, and we've done the hydrolysis of it. Remember, if we do acid hydrolysis, we form the carboxylic acid and the alcohol, whereas if we do the alkaline hydrolysis, we form the carboxylate salt. This alkaline hydrolysis here, this is an irreversible reaction, so once you form that, you can't go back by changing the conditions. Anhydride from the word an means not or without, and from the word hydra means water. So anhydride is a compound without water. The functional group of an anhydride consists of two carbonyl groups bonded to an oxygen atom. To name anhydrides, we drop the word acid from the name of the carboxylic acid from which the anhydride is derived and add the word anhydride.
The functional group of an acyl halide or acid halide is an acyl group bonded to a halogen atom. If we say halogen, we all know that halogens are known as salt-producing, mainly fluorine, chlorine, bromine, iodine, and astatine. An acid halide, also known as an acyl halide, is an organic compound derived from carboxylic acid by replacing a hydroxyl group with a halide group. Now, in naming acyl halides, they are named by changing the suffix ic acid in the name of the parent carboxylic acid to -yl halide. In this example below is an atom called ethanol chloride. We are going to discuss the process of how it's named. This molecule is a 2-carbon acyl halide. Now remember, if it was a 2-carbon alkane, it would be called ethane. from ethane, we must then treat it as a carboxylic acid. The key point for naming acyl halides is first, we must treat it as a carboxylic acid and then derive the acyl halide name. Now from ethane, it is now called ethanoic acid. Therefore, the acyl halide name of this molecule is simply ethanoyl chloride. We can also use the common name for this molecule. In carboxylic terms, this is called acetic acid. Now changing it to an acyl halide, it's now called acetyl chloride. To continue, the functional group of an amide is a carbonyl group bonded to a nitrogen atom. We name amides by dropping the suffix oic acid from the IUPAC name of the parent acid or ic acid from its common name and add amide in the end. As an example, the molecule shown in the table below is an acetamide, which is in its common name derived from a carboxylic acid. To name it, if this were a 2-carbon alkane, then it would be called ethane, but since it's an amide, we change it to ethanamide. Ethanamide. We are simply replacing the E in ethane with amide. Now, using the common name for this molecule, if it is a 2-carbon carboxylic acid, then it would be acetic acid. It then would result to its amide identity, which is acetamide.